The purpose of this video is to demonstrate how SEL's Synchro Central software identifies power system ring-down events using modal analysis. Central is able to recognize these events from real-time streaming data and can switch seamlessly to historical mode for additional analysis. In real-time mode, it indicates possible events within seconds of event initiation. First, we will describe data preconditioning, the settings and the MAA algorithm employed, and how these modes are indicated in Synchro Central as the event moves through the processing window. We will next show Synchro Central displaying a replay of one of the events in real time. Finally, we will show a more detailed post-event analysis of one event and summarize the data from all 5. The signal used for this modal analysis scenario is a frequency difference between the north and south station PMUs. The signal is further normalized by the standard deviation of the signal under ambient conditions. It is then passed to both the modal analysis engine and the alarms processor. Total least squares analysis of the Hankel matrix was employed using 42 search modes, of which the top 4 are reported. TLS was chosen because it provides better differentiation of event data from ambient than Prony and is less computationally intense than structured total least squares. This is a result of its better characterization of damping in ambient data. The modal analysis engine provides rapid detection within seconds of an event. When the event first enters the processing window, several red highlighted dots indicated that the MA perceives this as a growing oscillation. As more of the event moves into the window, the ring-down nature is identified and damping moves towards stability. Once the full event is in the window, accurate measures of event damping and frequency can be extracted. Here we have configured an overview display showing a representative geographic map with voltage magnitude contours, the frequencies for all 5 stations on the right, and the frequency difference between the north and south PMUs overlaid with alert and alarm thresholds at 7 and 15 standard deviations respectively. Here you can see the first event occurring. The oscillations are visible on the charts as well as the map. The differential frequency has exceeded our alert threshold, resulting in an activated alert annunciator over on the right. We can click on the annunciator to show additional information and to clear the alert. At this point, we'll skip to the second event and show some of the modal analysis information. On top, we can see the same raw frequency chart from before. On the bottom is our basic modal analysis display. The gray signal is the north-south differential frequency that we're using as our MA input. The colored dots indicate the frequency of detected modes. Here we can see the second event. The yellow and red highlights on the modal frequency dots indicate a combination of high amplitude and/or poor damping. These are caused by the leading edge of the event being perceived as a rapidly growing oscillation. These highlights quickly stop as more of the transient comes within the processing window and the ring down is detected. For more detailed MA analysis, we'll bring up a view with additional modal charts. This view includes MA dots plotted on various axes: frequency versus damping ratio, frequency versus log amplitude, and damping ratio versus log amplitude. Here we can see how the damping, amplitude, and frequency are identified as the event progresses. As the third event comes through, we can see the initially detected large amplitude and poor damping, which quickly work their way left and up to indicate decreasing amplitude and improving damping. Now we'll move out of real-time mode for further analysis of this third event. We're using a 15-second MA window, so first we'll adjust the display to show that time period. Now we'll slide the initial transient noise out of the window to focus on the ring down part. The dots corresponding to this window are available here on the right. We can see several repeated frequencies indicating that they are likely true modes. Here are 3 dots all around 0.6 Hz with damping around 15%. If we click to highlight this mode, we see its respective dots highlighted on the other 3 plots as well. This 0.38 Hz frequency has 4 dots, and this 0.22 Hz frequency has 3 dots. We also have a couple dots at 0.86 Hz. Now we go back to real-time mode by clicking on the clock in the upper right-hand corner. Green indicates real-time mode. Here you can see the top modes summarized for the 5 ring-down events.